Have you ever heard of a scientific theory that actually published its own hit list? You know, a list of experiments with actual deadlines that could kill the theory for good if they fail? It sounds kind of crazy, right? But it's probably the most courageous thing a theory can do. And today, we're going to look at one that's doing exactly that.
Okay, let's just dive right into this, because this one idea is the absolute bedrock of all good science. If you have an idea, and you can't even imagine an experiment that could prove it's false, then what you've got isn't science. It's a belief system. It has to be able to be challenged by cold, hard reality.
And there's a name for this, right? It's called falsification. Now, that might sound a little negative, but a theory's biggest strength is its willingness to stick its neck out there and basically say, hey, here's a very specific prediction I'm making. Go check. If you don't find it, then I'm wrong. That's scientific courage. And so, our case study today in this kind of scientific bravery is a theory called the single bulk framework, or SBF for short. Now, we're not here to argue that it's the absolute truth. We're looking at it because it is a perfect example of how science is supposed to work by literally publishing a list of all the ways you could prove it wrong. So first up on the hit list, the main event. This is the big one. The SBF makes this primary, totally non-negotiable prediction. It's the do-or-die test, the one that could bring the whole house of cards down in one go. So what is this ultimate fingerprint? Well, the theory claims that if we look really, really closely at the oldest light in the entire universe, the cosmic microwave background, we should find this very specific, kind of strange signature that, according to all our standard models, just shouldn't be there. And this is where the two ideas just completely diverge. See, standard cosmology, it predicts a nice, smooth, gently curving signal from the baby universe. But the SBF theory predicts, well, this, a jagged, totally unique sawtooth pattern. It's a completely different shape, a clear, unambiguous target. And the really critical thing here is the specificity. The theory isn't just waving its hands around saying, oh, it'll look a little weird. No, it is giving an exact address, predicting these weird peaks at very specific coordinates in the data. Physicists call them multipoles, L equals 4 and L equals 6. This is not a vague guess. It's a precise fingerprint, one that standard theories have absolutely no explanation for. And get this, there's a deadline. We are on the clock. Sometime around 2035, the LiteBIRD satellite mission will have enough data to make the call. It will either see that sawtooth pattern or it won't. That is the moment of truth. A clear verdict is coming.
Okay, let's move to the next test on the list, because this one's really interesting. It shows how sometimes finding absolutely nothing isn't a failure, but actually a really subtle clue. This one has to do with gravitational waves. So here's the situation. A bunch of theories, including some of the early ideas behind SBF, predicted that when two black holes smash together, there should be echoes in the gravitational waves that come out, kind of like the waves are bouncing off a hard wall at the event horizon. But our best detectors, like LIGO, they found nothing. Zilch, just silence. Yeah, this is where the theory does a clever little pivot. That lack of an echo, it kills the simple hard wall idea, but the theory adapts. It refines its prediction and says, okay, what if the boundary isn't a hard wall? What if it's more of a mushy zone? A soft boundary that would basically smear out and muffle any echo, making it way too quiet for us to hear, at least for now. So this creates a two-step execution. The fact that we don't hear echoes now is a soft falsification. It rules out the simplest version of the model. But the theory is not off the hook. Future third-generation detectors are going to be so sensitive that even a tiny echo from a mushy zone should be detectable. And if they still find nothing, that's a hard falsification. Game over. Okay, now we get to the really, truly ambitious stuff. These are the tests that are so difficult, they're way out on the horizon. They need technology that we're still dreaming up. This is the long game of physics. You might want to sit down for this one. The SBF actually predicts that the weird, spooky link between two quantum-entangled particles, what it calls a flux tube, should have mass, that it should have weight. It's proposing an experiment to literally weigh the connection between two things that are linked but miles apart. And the scale of this experiment is it's staggering. We are not talking about something on a lab bench. The proposal involves separating these two entangled objects by 1,000 kilometers, using satellites orbiting the Earth.
So what are they trying to measure across that huge distance? A predicted mass of just 10 to the minus 18 kilograms. I mean, that is an absurdly, ridiculously small number. To put that in perspective, that's roughly the mass of 500,000 hydrogen atoms.
So this is the big question, right? How on earth could you possibly measure the weight of almost nothing across 1,000 kilometers of empty space? It is one of the most audacious, bold, experimental ideas I have ever come across. But that's what a good theory does. It pushes us to even try to imagine something so incredible.
And if you thought that was mind-bending, hold on. The SPF also predicts that space itself has a limit, a physical breaking point. It suggests that there is a maximum possible strength for a magnetic field, and if you go past it, the vacuum of space will literally melt or break.
Just look at this bar chart. It really puts into perspective how wild this idea is. The absolute strongest magnetic field we know of in the entire universe comes from something called a magnetar. That's the tiny little bar on the left. The breaking point that SPF predicts? That's the skyscraper next to it. We're talking 42 orders of magnitude stronger. It's a number so huge, it's almost meaningless.
So let's bring all this back together. Why did we just go through this whole hit list? Because it gets right to the very heart of what science is supposed to be. It is all about having the courage to be wrong.
You see, a great theory isn't great because it's popular or because the math is elegant. It's great because it is risky. It makes these incredibly specific, testable predictions. It gives us a deadline for a verdict. It makes itself completely vulnerable to being destroyed by a single piece of evidence. And only if it survives that trial by fire does it earn the right to change how we see the universe.
The single bulk framework is bravely putting its own head on the scientific chopping block. And you know what? Whether it survives or not, its approach is a massive win for science. It really makes you wonder, doesn't it? What other beloved idea in physics, or any science for that matter, is next in line to face its own hit list?